Okay, so welcome to the last Hardware Systems Consortium talk of the quarter. And today we have Rajit Manohar from Yale. He's a professor there, an endowed professor. He does a lot of work in asynchronous logic and design. He's previously at Cornell, and he's previously done the startup at Acronic Semiconductor. So we've seen a lot of our students have actually done internships or joined there.
Oh, interesting.
I think 4 of my students have joined there in the last 2 years. Yeah.
Oh, wow.
So, yeah, so welcome, and I'll give you the floor.
All right, well, thanks for having me. Please feel free to, this is not ideal, but feel free to interrupt whenever you have questions and stuff like that. I'm more than happy to take that. And, Matt sort of gave me a bit of background so that, not too many people most people don't know a huge amount about asynchronous design. So I thought I'd give you sort of a little bit of an overview of asynchronous design, sort of why I work on this, why I think it's interesting, why there are what are some of the potential reasons you might want to do this. And then I thought I would end with sort of some of the bigger, the EDA challenges. So sort of mix of both design and EDA. My background is, we're always designing asynchronous chips. And of course, as you know, if you want to design anything non-trivial, you need CAD support. And of course, nobody supports asynchronous design commercially. So we were kind of forced into doing our own CAD tools. And that's kind of taken a life of its own at this point. So I'll talk a little bit more about what we've been doing on EDA. So with that, I thought I'd give you a very sort of, if you just sort of take computation in general, I can sort of divide computation into, these 4 big buckets, if you like, right? So there's the standard discrete time, discrete value computation, which we all know about, which is sort of digital synchronous logic. And I'm dumping multi-valued logic into this bucket as well. Then you've got sort of the discrete time continuous valued logic, which is what you think of as switch capacitor analog. And here's a really simple example of a switch capacitor analog circuit, typically used for things like DC-DC converters. You've got continuous time, continuous value, which is like an amplifier, right? So standard analog computation, that's a pretty common thing people do. And then in this quadrant, which is sort of, I would argue, not that highly explored, especially of late, is discrete value, but continuous time. And that's what I refer to as digital asynchronous logic. So if I think about an asynchronous computation, right? So what is the model that we use to think of a chip? So the model that we use to think about computation in the asynchronous domain is we think about a chip as a parallel program, okay? And the components of this parallel program, sort of the hardware blocks on the chip, if you like, are processes, right? So things that operate in parallel. So think message passing parallel programming, right? You've got blocks that correspond to hardware modules. You've got these little arrows that really correspond to communication links or communication channels. And the way processes exchange information is by explicit message passing, okay? So that's kind of the basic model. And so both communication is explicit, synchronization is explicit. So to synchronize 2 processes, they have to send messages to each other. And the fact that if process A sends a message to process B, then this can't proceed until if it's waiting for a message to arrive, then you know that this message has been sent, and that's the synchronization operation. That's the core primitive underneath, under the hood, if you like. So synchronization and communication and information exchange is all handled through message passing. Now, I'm drawing these sort of arrows here, right? But if I sort of unbundle these arrows really correspond to a collection of wires. And there's basically a very large number of possible ways a bundle of wires can be used to encode a communication action in an asynchronous computation. I'm showing you sort of the 2 most basic techniques, and these are actually widely used. One of them is referred to as a delay insensitive code. So here I have 2 wires to encode a bit and an acknowledge for flow control. So essentially what happens is if I want to send a 0, I would set this wire would make a 0 to 1 transition. Then I would get an acknowledge, and then I would reset this wire, and then acknowledge would reset. So you go, this wire goes high, this wire goes high, this wire goes low, this wire goes low. That's a 4-phase handshake, and that sends a 0. If I wanted to send a 1, I would do a 4-phase handshake on this pair of wires. right? So this is an extremely robust protocol. I can put any amount of delay on any of these wires and everything still works correctly, right? So it's a robust protocol, but you can clearly see there's a cost in encoding overhead in terms of wiring. Another very popular protocol is called the bundled data protocol. In this protocol, what happens is you've got request acknowledge. So this is used for synchronization. And then there's a collection of data wires that's used to acknowledge the data, but this protocol requires a timing constraint, which is that when I say there is new information, when the request goes high, the value of the data wires has to be stable. So the receiver can then correctly sample the data, right? So now that's a timing constraint. So this protocol isn't delay insensitive because if I put delays on these wires, I can break the communication protocol. So you have to be careful in the implementation, right? So there's like a whole range of these things depending on, there's a trade-off between how fast the protocol is, how wire efficient it is, and how robust it is to various uncertainties. Okay, so that's the basic idea. So each of these communication links gets translated into a link of this sort, and that's how the computation proceeds. Okay. So I hope that sort of basic stuff is clear. Again, any questions? If not, I'll just keep going. Right. Now, the big difference between the conventional clocked or synchronous computation and asynchronous computation is in a clock computation, the way I like to think about the difference is it's really the difference between explicit versus implicit synchronization. So what do I mean by that? So in a clocked or synchronous computation, essentially what you've got is time has been discretized. So I've got these discrete time windows. These are evenly spaced by the clock period. Okay, in the simplest world, you have a clock period that's fixed. By the way, this gets extremely complicated in a modern ASIC, but let's not worry about that for the moment. You've got these very simple boundaries, they're periodic, and different parts of the chip are doing computation in parallel, but any amount of work they have to finish has to be finished by this hard deadline, if you like, right? There's a global barrier that's enforced by the clock in terms of the computation, and all the computation has to fit within this time budget. Right? That's the way the computation proceeds. That's the basic idea. Right? So the benefit here is that this boundary, essentially anyone can read the result of any computation, right? So B2 could read the results of A2 or C1. It doesn't matter, everyone's done. And so you can think about this as sort of global shared variable synchronous communication. You know that the shared variables are stable when you sample them at the next clock edge, right? And those shared variables really are your state vector, if you like. Okay. As opposed to this in an asynchronous computation, what ends up happening is if a process is done early, the other parts of the computation that are waiting for these results can proceed as soon as the results are available, okay? So what ends up happening is you have this extra sort of, if you like, extra overhead for communication at the end of the computation period. But instead, you don't have to wait for the barrier to show up before you proceed with the next step, right? So that's the trade-off. So if this overhead is small enough and these gaps are large enough, then you might win. Okay, so that's basically the trade-off. So if your computation is nicely balanced and everything is perfectly uniform, then most likely if you convert into an asynchronous computation like this, you'll pay this overhead and not get much benefit. If on the other hand, the computation you're doing has a wide range of delays, right, then you might be able to close this gap and get a benefit, right? So that's sort of the pros and cons. Okay. So I thought I would give you a little bit of a historical perspective on what happened, right? So if you look in the early 1940s, so this is sort of the famous von Neumann architecture paper. Actually, in the blueprint for a von Neumann computer, they actually make a case for asynchronous, especially for arithmetic, it turns out, right? So you actually showed that building an adder, you should build it asynchronously. You're going to do much better on average, okay? So, and then there were a bunch of computers designed here that were mostly asynchronous. There was a nice book on switching theory written by Miller in the mid 50s that talked, there were 2 volumes and the second volume was entirely devoted to asynchronous design. Okay, so it just gives you some calibration for how prevalent this was. Some of the fastest computers in the world in the 50s and 60s were all designed with asynchronous logic, right? And then somewhere around in the late 60s, something changed. Okay, so there were these famous projects like macromodular systems. This is Wes Clark, one of the designers of the fastest computers in the world in the 50s. He was at MIT. This is Charlie Molnar. These are very famous researchers who made foundational contributions to the logic design and things of that nature. You recognize the name Huffman from Huffman coding. It's the same Huffman, by the way, and then invented something called Huffman flow tables for synthesis. And then right around here, essentially, there was, I would call this like this, about 10 to 15 years where there was like a gap in asynchronous design, if you like, until roughly the Mead and Conway book on VLSI design showed up in 1979, which had a chapter on what is called system timing, written by Chuck Seitz, where he advocated we should look at asynchronous design again. Okay, so, and then there's a huge amount of work starting from the early 80s and early 90s, and I've sort of color coded this. The gray stuff is, I'll say, more of a theory. There's a one-off here, which is an Ethernet switch chip. And then the red colored boxes are microprocessors, and these are all neuromorphic chips, so neural network chips. Okay, so it's instructive to think about what happened. Okay, so what happened in the 1960s? Now, the computer science is a funny thing where the discipline is young enough that there are people today who remember what happened in the 60s. Okay, so this, what I'm repeating is actually something I heard through some of the researchers working on computers in the 1960s. They said, here's what happened. Here's why we switched in the 60s, okay? Now, one of the big issues people were worried about in the 1960s was reliability, okay? And in particular, reliability in the presence of noise, okay? And this noise is like, noise on your wires, okay? So, coupling from, various EM signals and so on and so forth. And noise is an interesting thing. If you know about it, you can do something about it, right? So the problem that they encountered was unpredictable noise, okay? So to understand where unpredictable noise might show up in a computer system, here's a picture of the Atlas. Okay, this was a computer that was one of the fastest computers in the world at the time, designed at the University of Manchester. And this was their backplane, right? Now, these things were manually wired, okay, which basically means that no two backplanes were the same because these were run by human beings and there were slight differences in the wires. So actually, you had no idea where the noise was going to come from on any of your wires. And then somebody had a brilliant idea. They said, look, this is a mess. What we're going to do is something very simple. We're going to take one signal, the clock, and I'm going to prescribe exactly how this signal is run. It's going to be run very carefully, and everyone is going to run it in the same way on every backplane. And then everything else, we don't worry because we'll run the clock slow enough so that all the noise will settle down and then we can sample the state and everything will operate reliably. Okay, and that was like, okay, great, we solved this big problem. And, and that's kind of how everybody switched over to synchronous logic, essentially. So it's an interesting story because especially today we build these chips. These chips are built, we no longer build, well, I mean, I hope that we don't build backplanes that look like this. Although if you look at your data center, you may be a little scared. But at least at the chip scale, we no longer build chips like this, right? We tape out chips. They're designed with very high precision, so we actually know where all the wires are. So this unpredictable noise is no longer an issue. But of course, when they made this transition, that was when there was a huge effort in the computer industry, and lots of development occurred, and the sort of asynchronous logic was sort of kind of fell by the wayside, if you like. Okay? That's a bit of history. And that's sort of why, somewhere around here, people started looking at it again. And what I want to talk about now is sort of why one might, oh, that's interesting. Matt says that Huffman finished his career at UC Santa Cruz. I didn't know that. That's another interesting data point. Cool. So what I would say next, so what I'm going to talk about next is some of the reasons I'm looking at asynchronous design. Sort of what are the things that we are trying to exploit when we design things asynchronously, right? I mean, there are lots of synchronous systems out there. The vast majority of digital systems are asynchronous, are clocked and are synchronous. And so why would we look at asynchronous design? So I'm going to give you some flavor for what that's about. And the first big reason that people talk about, and I'm going to try to give you some simple examples in each case of chips that people have built where they actually exploited this gap. Okay, so this is not just a paper gap, but things that people have seen. So I'm going to use sort of the most famous example of this average versus max delay because it's easy to understand, and that's the famous example of binary addition, right? So we all know how to design binary adders, right? How to make them fast, so on and so forth. And the slow part in a binary adder is computing the carries, right? We all know this. And what's interesting about the binary adder, of course, is that, for example, if I look at this bit position and I'm adding 1 and 1, then I know the carry out is 1 without waiting for the carry in, right? So this is called the generate case, right? In a kill, propagate, generate adder. So there's the generate case and there's the kill case where I know the carry out without waiting for the carry in. So what if I initiated the carry out, right? So I can produce the carry out and then eventually consume the carry in, right? So that's my little optimization. If I know what the carry out is, I generate it without waiting for the carry in. And if you do that, it turns out, and this is actually a theorem from von Neumann in 1946, he showed that the average case latency for a ripple carry adder is logarithmic in the number of inputs, right? So that's kind of interesting because we know the worst case is order n in this case, but here you get, on average, you get a log n latency, right? So that was why they said, we should design arithmetic this way because with much fewer devices, we still get an efficient arithmetic block, okay? Now, you can say, well, that's all well and good, but we know how to design log n synchronous adders, right? So that's correct. We know how to do that. We use trees of various types to get logarithmic latency in the worst case. So the standard tree adder, you can get order log n latency. And there's actually a theorem from 1965 by Winograd, who was at IBM, who proved that the worst case latency for binary addition is in fact log n. You cannot do better than this. But that's the worst case. And the question is, what could you do on average? And it turns out that what we showed is, if here's my tree adder where I'm sort of propagating my carry calculation up a tree, if I do that in parallel with a ripple carry adder and simply take the result that shows up first, okay? So it turns out you can do a ripple carry adder at every level of the tree. And now at every stage, you've got 2 paths for a carry calculation. I can get my carry either from here or here. And if I just take the earliest one, you can show that this adder topology has an average latency of order log n. Okay, so this is now asymptotically better than you could do with any kind of worst case latency adder, right? So that's kind of interesting. And just as an aside, so I designed this adder and it turns out that the crossover point, right? So you could say, what's the constant factor issue, right? So the crossover point, it turns out, is luckily at n equals 32 bits. Okay, so at 32 bits, you actually get better latency than a normal, worst case, just a tree adder. But what's even more interesting is that you can actually prove that you can't beat this adder. So you can show that the average case latency of this adder is just as good as anything else you could possibly build, right? So that's kind of interesting. So you can actually exploit sort of the fact that you have data dependent delays in circuits to do better on average. So that's one of the big things people look at. So looking at the difference between the average and the maximum delay and seeing what you can do. Okay, so that's the first sort of big thing. A second reason people look at this is look at asynchronous design is trying to exploit data-dependent power management. Okay, and I'll give you a very simple example of this. So this is a paper from, again, 1996. So the idea was you were trying to design they were designing a FIR filter where the latency of the filter, or actually not the latency, actually the throughput of the filter depended on the data. So they had this interesting design internally where depending on what the data was, your circuit would be faster or slower, and as a result, you would get data dependent throughput. And what they did was they added FIFOs on the input. And now you can look at this FIFO and you can look at the occupancy of this FIFO, right? And if this FIFO starts filling up, that means that the FIR filter is sort of slowing down, right? So you have you've got a module here that inspects the state of this FIFO, and then this was connected to a DC-DC converter which controlled VDD for this entire domain to try to keep that FIFO sort of at a low occupancy rate. So essentially what they did was, what they would use is they would use VDD scaling to reduce the power consumption of this circuit in a data dependent manner, but while maintaining sort of a baseline throughput requirement. And this baseline throughput requirement was governed by an external circuit that was clocked, right? So you're getting data in at a fixed rate, wanting the results at a fixed rate on the output, and then you had dynamic voltage scaling based on the occupancy of this FIFO, right? So that was a very nice little trick. And so they used this to build a low power asynchronous FOR filter. And this was for a hearing aid. So that's another example of where you can use data dependent power management to improve the sort of the overall performance of your system or power efficiency of your system. Here's another example of a design that we did where we did data driven power management, and we built what we call width adaptive numbers. So what do I mean by that? So if you imagine trying to do an arithmetic like this, right? We're doing, if you're doing a normal, ALU, you're doing arithmetic with all these zeros up here, right? So instead, we used a number representation where, along with the digits, we had extra information that told you that the number ends at this digit, right? So here is 0, but there are no more digits that are more significant than it, right? So in other words, we've sort of, if you think about this as run length compressing of the most significant bits of the number, right? And so in the asynchronous case, we sort of built the data path so that essentially you wouldn't even send the high order bits, right? So if I'm a sender and a receiver, and I'm only activating this section of the data path, and you don't even ever send information on the high order bits, and you don't trigger any activity. And we actually built a full CPU like this, it turns out. You can actually do this for the whole data path. And what we showed was that, if you look at various, spec this was an old paper, so we were using old versions of the spec benchmarks. You can actually, on average, even on a 32-bit processor, you end up using something like 8 to 10 bits on average. And looking at different schemes to look at how you could compress this information and so on and so forth, it turned out that you could actually do a very good job. What was very interesting about this paper, by the way, is, this was kind of buried in there. But it turns out that if you did your design this way, it would actually make the worst case performance worse, right? Which you should expect. There's going to be overhead in looking for this sort of, end of the digit, end of the number, for example. And that's going to increase your logic complexity, right? So if you did this in a clocked implementation, it turns out it's a bad idea. It's just better to just reduce VDD and you would get better energy efficiency. But in this particular application, because it's asynchronous, it turns out that because you can get a faster result in the cases where there are lots of zeros, on average, you still did better. So it's sort of an interesting example where you do an optimization that actually is a bad idea in the clocked domain, but it's actually a good idea in the asynchronous domain. The third category of reasons people look at asynchronous design is what I'll call exploiting the elasticity of pipelines. So what do I mean by this? So if I have a clocked pipeline, a traditional clock pipeline, when the clock shows up, sort of you're doing some computation in these 3 different pieces of combinational logic, and the data from one moves to the next, and so on and so forth, right? This is a pretty standard synchronous pipeline operation. In an asynchronous pipeline, because we don't have these explicit flip-flops here, so what you end up having is you've got data flowing through the pipeline, and the data tells you when it's there. So you have a notion of an empty pipeline stage. Now you can emulate this in the clock domain by adding valid bits and tagging all your data, if you like. But those tags essentially are always there in the asynchronous pipeline. And as a result, you can do things like change the number of pipeline stages here without affecting whether the computation is correct or not. So you can dynamically repipeline the circuit, and you can use this to get some interesting behavior, right? So an example, this is actually from IBM research, is a FOR filter where they actually had, again, this has a clocked environment. It's got an asynchronous pipeline that's sort of surrounded by latches. But the occupancy of this pipeline, the number of data values in flight in this pipeline, is data dependent, it turned out. Okay, and the reason was this was for a disk drive controller. There's a FOR filter attached to a disk drive, and depending on where in the platter you were reading, the data rate would be different, right? And as a result, they had to do this very complicated sort of adaptive management. And they said, well, instead, we can just put an asynchronous pipeline here. And then I can just keep track of how many tokens there are in the pipeline stage. And I can basically figure out exactly how many things there are. This is a fixed latency pipeline with a variable number of data items. Okay, so you've got a variable number of clock cycles in your budget, but with a fixed circuit and nothing fancy on the control. So they built this. They found that doing this got them better power and performance than any of the other approaches they had tried. And this is kind of, they actually shipped this to all their customers. This was one of the last disk drives IBM made before they sold the entire hard disk division, I think, to Hitachi. This was a while back. Another example of exploiting the elasticity of pipelines is an FPGA architecture that we designed. Here, the idea was we could pipeline the interconnect. You could have pipeline repeaters in the interconnect. And the fact that there was a pipeline stage there didn't change the computation, right? So I didn't have to worry about retiming the logic when I added pipeline stages in the interconnect. And as a result, you could actually put pipeline stages wherever you wanted, and you could improve the throughput of the FPGA. In the case where you were mapping sort of feed-forward applications, it would run really nicely on the architecture. Now, one of the things I haven't really talked about too much is, but I hope it should, you can see why this might be the case. In an asynchronous circuit, the delays are going to be dependent on the delays of the devices that are being used, the gates and the transistors used to build the gates and so on and so forth. So if you change VDD, for example, or you change the operating temperature, the device characteristics all change, so all the delays change. But if you built your circuits to be robust to delays, and certain asynchronous circuit families have this property, then you should expect that the circuits are going to be completely robust to process variations and temperature variations. I mean, within limits, of course. I mean, if your inverter no longer behaves like an inverter, of course, the circuit's going to fail. But as long as it still behaves as an inverter, logically, then everything can still work. And so we sort of tried this experimentally, and we took the FPGA that we had built, and we actually tested it at a wide range of temperatures and voltages. And we showed that essentially the chip can run from 400 Kelvin to actually all the way down to 12 Kelvin. And you can change the voltage while the chip is running and everything still works and so on and so forth. So you could imagine using something like this for building cryogenic electronics. And we're actually doing a little bit of that now. So that's another example of timing robust, where you can use timing robustness for building, for doing interesting things. Another place you can exploit timing robustness is trying to get your circuits to run really, really, really fast without worrying about timing margins as much as you would have to do in the clock domain. So this is a logic family that was developed by Ivan Sutherland. And they designed this logic family. They came up with a fun acronym called GASP. And the idea was, you should gasp at how fast the circuit's running. And they developed this very nice logic family with no margins on control signals with a standard data path that can run at roughly 6 FO4 cycle time, which is, it's basically hard to do better than that and have your circuit still oscillate. So just to give you some calibration, they built a 640 nanometer chip that operates in excess of 6 gigahertz, right? Without, and by the way, this is without any fancy CAD support, right? Remember, I said this earlier, this CAD tool support is minimal. I'll talk a little bit about that. So this was all done manually, right? So they can't really do any fancy verification or anything like that. But they still managed to show that the chip can run at an extremely high frequency. There's another group of people looking at mixed signal circuits using asynchronous logic. And here they're trying to exploit noise and EMI. And this is a paper from Philips Research where they basically showed a ADC51 that they had built in-house before that was clocked. And then they did an asynchronous version of exactly the same chip. And then they looked at the time domain, the time domain response of the current, for example, and basically power, and then EMI as a result is derived from that. And you can tell this is an industry paper because there is no y-axis. They didn't tell you what the actual numbers were. The x-axis is time, and the y-axis is arbitrary units, I guess. But they built this because they found that they could actually get very low EMI, so they could actually tightly integrate this with they reduced their packaging costs, and they could tightly integrate the analog and digital electronics together. If you're an analog circuit designer, the clock is considered a noise source, and so if you have much smoother switching activity through the chip, then don't get me wrong, you have to worry about the noise, but it's less of a concern. The magnitude of the problem is significantly diminished, and you can actually cut a lot more corners. So that's another thing that people were looking at. And finally, the last category of reasons people have studied asynchronous design is to actually take advantage of continuous time information processing. And this is sort of my favorite example of this. So this is a chip designed by Yanis Savidis' group at Columbia. This is an ADC and with a DSP, and it's a continuous time digital signal processing engine. So normally when you have a signal, you sample it periodically in time, right, with Nyquist sampling. You get samples, you do your usual DSP. This is a signal processing engine where instead of sampling in time, you sample in value. So you get a sample when the signal crosses a threshold. Okay, so you get non-uniform sampling. And what you can show mathematically, and there's actually a famous paper by Rice from the 40s that shows this, is that you can show that what the number of samples you get with this scheme is equal to the local Nyquist rate. Okay, so you actually get enough samples to reconstruct the signal. And with this implicit representation, you can actually do direct signal processing. You can build a DSP with this. And what you essentially get is a signal processing chain where if your signal isn't changing in time or is very low frequency, it automatically adapts, it's bandwidth adaptive. It'll automatically sort of reduce the activity rate. And another interesting bonus is that because you're not sampling this analog signal, you don't get any in-band aliasing from sampling. Okay, so you get low noise because you don't get the aliasing effects because of sampling. And then you get this interesting bandwidth adaptivity to reduce the power consumption. So this is a large, I hope I've given you a number of reasons why asynchronous design is interesting and a number of examples where people look at asynchronous design for a variety of reasons. So you can say, okay, that's great. So you've convinced me I want to design an asynchronous chip for a specific project. So how do I go about doing this, right? Well, not so fast. Okay, so anytime you want to design anything non-trivial that's digital, of course, you need CAD support, right? You're not going to manually do these chips. You're not going to do full custom design. Well, not if you hope to finish in any reasonable time frame. So it turns out that this is actually a huge problem. So in about 2018, if I tell you, if I look at what the state of the world looked like in 2018, and I looked at what tools were available for asynchronous design, first of all, you look around and there's nothing is really available. Okay, there are a few small projects that you could sort of find point tools for, but nothing like a CAD flow for asynchronous logic. Okay. And if you look very carefully, the asynchronous community is really small. I know a huge number of the people in the community, I think, at this point, having worked in it for so long. So that you can like talk to each other and figure out that nobody has tools, okay? But there were a few groups that had in-house boutique tools, and these tools could be used for small circuits, primarily logic synthesis, not much more than that. And typically just for the particular asynchronous family they were investigating, okay? There were some in-house tools for custom design of large asynchronous circuits. So again, not a full ASIC flow, but if I wanted to sort of do a sort of an analog style design where I draw schematics and then I do layout and then I do DRC, LVS, simulations, all of that kind of stuff, there were tools that would allow you to do that. And actually my group had probably the most complete set of tools for that particular purpose. If you want to design something large and try to get something that looks like an ASIC flow, then what people were trying to do is basically trying to twist the arms of commercial tools to do what they wanted to do. And that essentially was a complicated battle, let's just put it that way. First of all, for logic synthesis, at least for control, there was no solution. So for logic synthesis, what would happen is people started switching to families which always, so there are some asynchronous circuit families where the data path of the circuit can be just straight combinational logic. Combinational logic is combinational logic. I can use commercial tools to optimize that for me and even do the layout for that for me. So people would do that. They would use logic families with standard data paths. Okay, turns out you can do that. You'd end up giving up some of the advantages I mentioned earlier. Okay, the other huge issue was that the timing was just not correct, right? The way the tools estimated timing, delays, all of this stuff, and they calculated the performance of your system, that was just not right. And why? Because in an asynchronous circuit, you have these handshakes. These are cycles of gates. There's no flip-flop to cut your cycle. which means all your CAD tools are extremely upset, right? It's like, I have a cycle of gates, I don't know what to do, right? And so people would manually cut those cycles, right? So saying, okay, cut this cycle, delete this timing arc, so on and so forth with fancy scripts. But what the net effect was that you had inaccurate timing, and this actually impacts everything, okay? Including your timing verification, right? Which is kind of a problem. Turns out that to implement asynchronous circuits efficiently, there you need non-standard state holding gates, okay? So not just flip-flops and latches, but you need other state holding gates to implement the asynchronous circuits. Otherwise, you're going to just pay a huge price in technology mapping. So if I have a non-standard state holding gate, then my CAD tools are even more unhappy, right? The commercial tools. And then the question is like, what do I do about SRAM, right? Like, I mean, almost any non-trivial ASIC is going to have a bunch of SRAM on it. And how do I build this, right? So, good question. So the answer to most of these things was, well, for SRAM, the answer was, I'm going to do full custom layout, and that's it, right? And people did that. Okay, so hope you can see that this is not any way to design a chip in any kind of reasonably efficient way in terms of, at least in terms of effort. Okay, and that's kind of what people were stuck with. So just to give you a flavor for the range of asynchronous circuit design styles and the kind of assumptions you need to worry about, especially in terms of timing. So here, this is sort of my, this is like my sort of sampling of asynchronous circuit families. There are many more, by the way, but I'm not even going to go there. But what I wanted to share with you is sort of what are the sort of things you need to worry about for correct operation. So this circuit family is extremely friendly. It's delay insensitive. The gates can have any delay as long as the gate delay is in the range sort of 0 to plus infinity, and any finite delay is fine for the gates. Any finite delay is fine for the wire segments. So this is great. I have to do no timing verification. I mean, maybe I'll worry about performance, but at least my chip will work, right? That's kind of critical. Unfortunately, it turns out you can mathematically show that this class of circuits is extremely limited. You can't really build very much that's interesting using this approach. So the next compromise is QDI, or not quite, think of this as not quite delay insensitive. So here gates can be any kind of delay, but there are certain wires that have certain timing constraints that you have to verify. So it should be no surprise to you that most of the chips that were built that were actually worked correctly are primarily from this logic family, okay? Or at least all the control logic is from this logic family. There was another family called speed-independent circuits. These were popular in the 80s, where they made the same assumptions about gates, but they said that wires have zero delay. Well, wires don't have zero delay, so that was not exactly a great assumption. It was probably okay in the 80s, but certainly not now. So this kind of got sort of left by the wayside. And then there are a whole bunch of other things where you make delay assumptions and so on and so forth. So my point is, you've got circuit families where you're starting to make different sorts of delay assumptions on gates and wires, especially once you get to the time circuit family. So like the fast circuits are all in the time family. And now you've got all these very sort of interesting delay assumptions that you've made, and you need to verify them. And not just verify them during logic synthesis, but post, place, and route. Okay. So how do you check all of this stuff? This is a kind of a big issue. So this is probably the biggest issue in asynchronous circuits, getting the automation flow growing, okay? So what I'm going to share with you sort of quickly, I mean, I have about a little more than 10 minutes, I think, left, if that's right. I'm going to sort of give you sort of a quick tour of the sort of the exciting things you have to worry about for CAD, or design automation, in the asynchronous context. So I'm going to just start from logic synthesis, and I'm going to sort of show you all the steps. So it turns out logic synthesis, there are actually two pretty mature approaches for asynchronous logic synthesis. And what's nice about these logic synthesis approaches is these synthesis approaches don't depend on the circuit family. Okay, so you can think of these as synthesizing the circuit into small building blocks, and you build those building blocks depending on your circuit family, and then you're done. So that's pretty nice. It's sort of a more technology independent or circuit independent approach. There's what I'll call the control-driven approach. This was called syntax-directed translation. This was the first approach developed. And the idea here is you take the syntax of the behavioral description of the circuit, literally the parse tree, if you like, and use that to build the circuit topology systematically from the description of the logic. So you can think of this as sort of the simple code generator for a compiler can be written like this. And it's the same idea. In fact, they use the same word, syntax-directed translation, because that terminology comes from the compiler literature. So it's sort of a recursive way to build an asynchronous circuit. So for example, if I do A followed by B with a semicolon in between, then you have some module that implements a semicolon. And then you say, I do A, I wait for A to finish, then I do B, wait for B to finish, and that's when my module finishes, right? So that's sort of the setup. I wait for the signal to say, start running. I do A, I finish A, I do B, I finish B, and then I say, well, I'm done, and that's done A followed by B. And you can sort of take this to the extreme, and you can literally build everything like this, okay? In fact, in my class on asynchronous circuits, I actually have the students implement a synthesis engine using this kind of approach. And this isn't a terrible idea. It turns out that a full commercial flow was developed by using this approach by Philips Research. And they used that to build a bunch of product chips, but then they sort of, it fell by the wayside and they ended up doing other things later because, some of the people from that group sort of left Philips and then, sort of was sitting there. So unfortunately, I actually tried to extract this flow from Philips because that would have been a very good starting point. But unfortunately, they didn't do that, didn't provide it. An alternative synthesis approach, which is also quite mature, is what's called a data-driven approach. So in this approach, you take your behavioral description and you can actually decompose this into a data flow graph. And then you can build each data flow component using asynchronous logic, and you end up essentially getting a static data flow machine. So you get a static data flow graph, it's all implemented with asynchronous logic, and it turns out that this is also a pretty mature way to do things. And so this approach usually gives you much smaller circuits, much more power efficient circuits. And this approach gives you usually very fast circuits, but pretty power hungry, depending on how you do it. Okay, so that's another trade-off. So I'm not going to touch on logic synthesis. What I'm going to worry about is actually the implementation flow. So how do I take my gates and actually build my chip, right? And a clock flow has some standard steps. You normally use a memory compiler to build your memories. You specify design constraints, you use a cell library, and then you run through the place and route flow, right? And a lot of these things actually are provided to you by the foundry. Well, we don't have any such luck, okay? So we have to deal with all of these problems. So we are actually currently developing a full ASIC flow that's being built with which supports all the differences between sort of the standard synchronous flow and what we need for asynchronous logic. And the biggest thing that is different, really, I would argue, is timing. Okay, so we have our own memory compiler. We support more general gates. It turns out this impacts placement, but the key thing that we have to build is a very sophisticated timing analysis engine. And the flow that we're developing is sitting on GitHub. It's open source, so you can get it if you like. So I wanted to spend most of the rest of the time on sort of talking a little bit about timing analysis to give you a flavor for the complexity of the problem. And to just illustrate this, let's say I just have a simple ring oscillator, right? This is my simplest asynchronous circuit. It's just an oscillator, right? Now we capture the fact that this is a couple of a ring oscillator with something which was called a repetitive eventual system. So think of this as the timing graph, okay? So you say X goes up, then Y goes down, then Z goes up, then X goes down, then Y goes up, then Z goes down, and then this is my delay, right? So this is my sort of dependency chain. And I have one little difference. So there's a cycle in this graph, right? Which is what people are not used to seeing in a timing graph. And there's a little tick here. And this tick tells you that this is the connection from one iteration to the next, which means that this is the initial transition. So I go from X up to Y down to Z up to X down to Y up to Z down. And then in the next iteration, and then this repeats. And so really what this is a finite representation of sort of an infinite sequence where it's X up 0, right? So it's to Z down 0, and then I go from 0 to 1, and that's what this tick is capturing. So I go from one iteration to the next, and then this repeats, okay? And to figure out the timing in this very simple example, the way I do this is I say the time of this is going to be the time of this plus 2 units of delay. And if I have multiple incoming arcs, I'm going to say the time of this is the max of the delay constraints provided by the incoming arcs. So you end up having something called the timing function. So this timing simulation tells you exactly when a particular event occurs. And that's going to be the max of its predecessors plus their delay for every timing constrained arc. Okay, so that's the basic idea. That's how timing analysis works. Except I have a cycle, right? So I have cyclic timing analysis. So that's what I have to worry about. So it turns out that there are some theoretical results that have been independently discovered by 3 different communities, it turns out, one of them being the pure mathematicians. Roughly at 1990 and prior, basically the following analysis was done. So you have some sort of complicated timing graph with these cycles and ticks and so on and delays. Now, there was a postulate that says that let's assume that the circuit's periodic. Okay, so let's say that the ith occurrence of x occurs at I times p. This is my think of this as my cycle time plus some offset that doesn't depend on I, right? So if this is the case, then I know that my system is periodic. But it turns out that the system is not periodic. Okay, it's only approximately periodic. And the main result was essentially that the difference between the actual time and this linear approximation is fixed. Okay, it's independent of I, which means that this period tells you on average the frequency at which that signal is going to change, and that tells you the performance of the system. And it turns out that you can actually figure out what this P star is. It's what the algorithms community calls the critical cycle mean. Okay, so what does this mean? I take every cycle in my system, I sum up the delays along the cycle, and I divide by the number of ticks. Okay, so I take the max for every cycle in the system of the sum of the delays on the cycle divided by the number of ticks on the cycle. So you calculate this for all cycles. That's an exponential number of cycles, but it turns out that there's an efficient algorithm to do this developed by Karp in the early 80s. Okay, so you can calculate this algorithm, this algorithmically, and that tells you what the performance of the system is. So in this simple example, this is the critical cycle, and the cycle period of the circuit is going to be 20. So it's not going to be always, everything is not going to be perfectly spaced by 20, but on average, things will be spaced by 20. Okay, that's what it tells you. Great. So we built a timing analysis, but remember, we want to build a timing analysis engine that tells you when everything occurs so that you can calculate timing constraints and when things can occur. So this approximation isn't good enough. So we actually made a theoretical advance, and what we showed was that after some initial transient period of the circuit, it turns out that even though the circuit isn't exactly periodic, it is an unrolled version of the circuit is periodic. So there is some integer unfolding of the circuit where the events that are spaced m apart are in fact exactly periodic. Okay, so we actually proved this. This is a pretty messy mathematical proof. It doesn't matter, we showed this result. So now I can calculate m, I can calculate p star, and then from that, I can actually figure out the timing in the steady state for every transition in the system. I can verify all my timing constraints because now I don't have bounds on the delay, I have the actual time. The second complication to try to make this a real timing analysis engine is how do we calculate delays? So now if you know how the standard delay model works, and this is even an older model, not a modern model, but it's a pretty popular model. Sometimes it's a nonlinear delay model, is a table lookup delay model. It turns out that the way they calculate the delay is they take the delay as a function of the load of the driving load of a gate plus its input slew rate, right? So you need the pair of the load and the input slew rate, and the output slew rate is also a function of the input slew rate, right? And the delay of the output. But I have cycles, so how do I calculate the slew rate? So it turns out that what we observed, this is just an empirical observation, we can do this some analysis to show that you expect this to be true in general, is that if I pretend that the slew rates are sort of wide, they very quickly converge, okay? So we found that empirically, if you propagate the slew rate through 3 or 4 stages of logic, it becomes extremely narrow, and then you can actually figure out what the steady state slew rate of every single transition in your circuit is by just pretending that the slew rates are very wide apart, and you just run slew rate propagation, and it very quickly converges. So from that, you can figure out the steady state slew. From that, I figure out the delay, and then I can do all the calculations I need. The other thing we had to do, I'm glossing over like years of work for some of my graduate students. The other thing we have to do is calculate characterize gates that are non-standard state holding gates. So we built our own timing characterizer that we can characterize gates. We can characterize state holding gates like this one. This is a C element where it holds state if the inputs are different. So you have to be careful when you characterize the timing. So we build timing, we build a standard synopsis sort of .lib files for all our building blocks as needed. The third complication is this notion of these arcs having ticks. The ticks are not a function of your gates. The ticks are a function of how the gates are used and how the circuit's initialized. So you can see that these gates are all the same, but only one of these arcs has a tick. So you can't actually get these ticks from the timing library. So you actually have to compute the ticks. And it turns out that the way you need to compute the ticks in the published results on how to compute ticks involves simulation. And it turns out that the simulation takes so long that you could just use simulation and forget about timing analysis. Right. So we had to implement came up with a new algorithm to do this very, very efficiently. So we do that as well. And then to make this run in a reasonable rate, we actually had to parallelize the timing analysis engine so that it can run in a reasonable time frame. And this is because we use something called the Galois framework. This is a framework developed by UT Austin for graph-based parallelism. It turns out it's very nice. And the reason it's very nice is they did a huge amount of work, sort of systems hacking, if you like, making sure that the runtime system was efficient. So they deal with issues like lock contention and load balancing and work stealing and all of this stuff for you under the hood. And so we are working with UT Austin on this project, and they actually helped us get this timing engine parallelized. And it turns out that the runtime for the timing engine, even if we parallelize it, is significantly higher than the clock version. So just to give you some idea, if you have a benchmark with roughly 5 million pins, that even the parallelized timing analysis engine, we actually get pretty good speed up for parallel timing analysis, but even the parallelized timing analysis engine takes about almost 3 minutes for initial full-blown timing calculation and checking all the timing constraints. And that's actually a lot. If this were a clock circuit, this would be almost a factor of 3 or 4 smaller for a circuit of the same size. And there are many reasons for this, it turns out. It's just the amount of calculations we have to do is a lot more. Okay. So, but this is still, even though this is not great, it's still acceptable. By the way, the previous timing analysis results for a circuit of this size that was published in DAC about 3 years ago was 15 hours. Okay, and we can do the same circuit in about 2.5 minutes. So there was a lot of optimization we had to do. The last thing I'll talk about, and then I will pretty much stop there, is one of the things that we try to do to improve the placement. So one of the fun problems that you have in asynchronous circuits is you don't have, in combinational logic, you've got P's and N's as complementary. You expect roughly the same number of P and N transistors for any gate. In asynchronous circuits, we have very asymmetric gates pretty often. And so if you just looked at the placed and route standard cell version of an asynchronous design, you'll see lots of white space because a lot of diffusion area is wasted. And so to deal with this problem, we sort of benchmarked this before, and we realized that there's a huge gap between full custom and standard cell design in the asynchronous context. So we said, well, can we bridge the gap a little bit? So we came up with this approach that we call gridded cells. So think about a gridded cell as a standard cell, except we delete the power and ground rail. So we get rid of VDD and ground. We get rid of those buses. And then the height of the cell can also be an integer multiple of a routing track. So we can have very flexible cell sizes, both in the X and the Y direction. And so we actually built a placer that does placement using these gridded cells. And to sort of give you a flavor for what you look like, you run global placement, you get some mess like this, then you legalize it, you get detailed placement. And we start sort of grouping cells together into mini rows, and then we legalize them in these mini rows. And then we actually make sure that we actually fill in all the wells. So you legalize all the wells, and we add all the fillers, and we add all the well taps automatically. So you get these sort of interesting circuits where you got these little rows, but actually the rows are of different heights, because we just grouped the rows based on the global placement. And what we showed was that actually we get about a 10 to 20% reduction in area for about the same wire length for a circuit that has exactly the same sizing, everything is the same, right? So it's the layouts will LVS against the same netlist. And we save about 10 to 20% in area depending on our benchmark. So we actually developed this placer to improve to get rid of the overheads that we saw in standard cell place and route for asynchronous design. And a subject that's probably close to Matt's heart is a memory compiler that we built that's based on OpenRAM. So we started with OpenRAM and we said, well, we need to make the interface asynchronous. And so essentially what we have is, instead of the sort of the standard address data clock interface, we've got address data in, data out. That's not that different. But then we've got the handshake signals, request and acknowledge, that are used to trigger the memory operation. And something cute that we did was we did something that we added a read modified write cycle. So while the decoder is still driving the address lines, we can read the value and then overwrite it with the new data. Of course, you would never do this in the clocked implementation because it would make your cycle time worse. It would have, okay, but for us, it doesn't matter. The reads are still cycling at the read performance. The writes are cycling at the write performance, and the read modified write is slightly slower than doing a read, and that's fine, right? So you get but it's much faster than doing a read followed by a write. Another interesting feature that we added to OpenRAM, to the baseline OpenRAM implementation, was we added sub-banking. So you can sort of see that, you know, this is a 28 nanometer layout. You've got sort of the decoder. We have a second level of drivers, which are repeated for each sub-bank. And this allows you to effectively get the same effect as a hierarchical word line. And as a result, you can sort of, you pay some area, but you could get some power, and improve power and performance. And we've actually gone through a lot of pain and suffering to try to work through all the design rules for 12 nanometer. That seems to be working now. But that's sort of what we've been, so with this, we have a memory compiler we can use for our chips. I don't have, actually, I'm going to say one thing about this because this is actually a very interesting feature of this memory. You've got the address coming in that gets routed to a particular memory bank. So let's say this is a 16-way bank memory. We've got 2 levels of banking here. What's interesting is because this design is asynchronous, if one address gets routed here, that address could be still being processed here while the next address gets routed to a different bank. So if you're striping the memory accesses across the banks, you can actually get a higher effective throughput compared to how fast the banks itself can run. So you can actually get this memory to sustain the throughput that's determined more by the bus interface speeds rather than the bank throughput. And that's what we did for this memory. And as a result, we can actually run these memories at a very high frequency. So at least in 65 nanometer, as far as from our results so far, it looks like we can run the memory at over 2 gigahertz, which is not so easy to do if you had to hit this timing in all possible scenarios. And what our plan for doing next is actually to work with Matt and his group to try to integrate all of this into OpenRAM and see sort of how we can build a unified memory compiler that could target both synchronous and asynchronous logic. So I'm not going to talk about the current status of the flow. We've done there's a lot of work I've sort of summarized here, but we've actually taped out a bunch of chips with all the tools that are sitting on GitHub right now. This summer, we taped out our first 65 nanometer ASIC. We use Cadence for the detailed routing. Everything else here on this chip was done with our own tools, which are either open source or will be open source as soon as the paper eventually gets accepted with one of my students, so that my student can actually write a thesis. So that's where we are, and I'm going to stop here since I'm out of time. I hope I've sort of convinced you that there are some interesting reasons we're looking at asynchronous design. We're working on the EDA challenges, which are actually pretty significant, but we've got a good handle on them now. And really, I should thank everybody who did the work. By the way, people may not realize this, but I actually wrote the core infrastructure for all the tools. So the whole design language and the whole framework that scales up to like big chips. So I mean, I wrote all that code. You'll see I'm probably the most frequent committer to our GitHub repo. I think Matt and I share that. So with that, I'll stop and I'll take any questions. I'm sorry to run a bit over.
Yeah, if any students want to ask questions, you can type them in the chat and we'll answer there. So
while they are having some question. So, and it's something because I work in something that it can be interfaced, but I have not seen it, or maybe you have done. So there are some elastic pipelines concepts that you have, but from a more synchronous kind of point of view. So you can design systems in which you have the handshake when you do the specification.
That's right.
So in your case, you are I'm assuming that you get more Verilog kind of design, and then you convert with your flows to make it asynchronous. But you could have the full specification being with an asynchronous pipeline.
That's right. And actually, so, yeah, that's correct. So actually, my design language has an asynchronous specification. Yeah. So we actually use Verilog.
So you, I didn't see that language. So
yeah, no, I didn't. Sorry, it's like I had too many things to talk about. But yes, it's on GitHub. I mean, I can.
So in your case, you have your own language to specify. It's not that you get Verilog and you convert to the asynchronous.
That's correct. We have an asynchronous specification format, and we can actually export to Verilog. So the chart I didn't show you, we have our own design language that's called ACT. We can actually import a Verilog. So ACT is an interesting language in itself, but I mean, I could give you like a 3-hour talk on ACT itself. But it's a language that has evolved from literally from 1990 to today. Okay, so we can actually import Verilog netlists, but we can also export our design to Verilog from, after elaboration and so on and so forth.
But if you input a Verilog netlist, does it have to have the handshake for the handshake, or that netlist can be synchronous?
This netlist can be anything. This netlist can be synchronous if you want, but this netlist import is at the gate level. Okay, so this is not this is not something you want to work with. This is just something we have in case you've got some other flow which is targeting Verilog netlist for backend. We can suck it in and do the backend correctly for you.
Okay.
Right. So this import is really for other groups doing async design who are trying to use Cadence, for example, to do that place and route, and are killing themselves to get the timing stuff working. So we can just suck in their output of their flow and run it through our place and route flow with doing the timing properly. Right. So that's what this path is for.
Yeah. So I'll check the syntax for the language. So we have an alternative to Verilog that we are working.
Interesting.
And the thing that's a little bit connected is that we support elastic handshake on the language. And the reason is because we are working more for synchronous, but the idea is that then you can do more transformations on synchronous, but you still have like a handshake between blocks.
Right. So we have in our language we have something called a channel as a first class data type, which supports send and receive operations and certain other operations on the channels. And then it turns out that we can actually support both synchronous output on implementation of the channel with ready valid if you want, and we can support asynchronous implementations of the channel as well.
Yeah, in our case we only do synchronous, but technically it could work as synchronous too. Right. And the concept is more like an actor model.
Okay.
And then you communicate with channels with the other blocks, but they restart the flock. So it's more like an actor based.
I see. So you do like a remote method invocation effectively through or do you do it?
It's a little bit hidden and it's different, but it's like from a high level, from internal point of view, it looks like an actor model.
I see. Yeah, I mean, people always ask me why I don't use Verilog. It turns out that the language that we use for hardware description predates Verilog by like 2 decades. So I mean, I always joke saying, actually, the language we're using first. So, sorry. And it's been used in the async community since like the late 70s. So it's actually based on Tony Hoare's CSP language, for those of you who are familiar with it.
I had one question about the timing analysis. You've mentioned basically like slews and loads, but things like noise coupling between wires, things like that. How it seems like when you need to compute like this P star you're talking about, that if you have all these external effects,
right,
that can affect that value, that would be very complicated.
Yeah, I mean, it's basically, so if the way to think about it is, right. So we actually have a noise analysis too. I didn't talk about it, but we actually compute the noise on the coupling noise on every gate. Actually, so we've got a tool to do that. But so there are 2 ways you can view that. So there are 2 things we have to do for noise analysis. I mean, it's a great question, by the way. It's something that keeps me up at night sometimes. But there are 2 things we have to worry about for noise. One of them is the noise high enough that a signal may be interpreted as a signal transition by a downstream gate? To me, that's a fatal error, right? So you have to guarantee that does not happen. And so that's one piece. right? So that's just just think of that as electrical rule checking, really, right? But then there's a second piece, which is how does this affect the delay, right? So this is not implemented yet, okay? So this is what will hopefully be added to the timing analysis engine, because you essentially if you think about what's happening, the circuit's running, and at runtime, you know what the noise is, right? So without knowing the timing, you don't really know what the noise is. So it's a coupled calculation. So what you need to do is you need to do the timing analysis and noise in one pass, coupled. So that's what's going to have to happen. And by the way, that's actually why we do the power analysis at the same time as timing, because we're already doing what we need for power. But we need to add coupling to the pass as well. That's a great question. But yeah, that's how we would handle it. But I mean, well, you can start by being paranoid, by just saying, well, I'm going to just do worst case on the delays. I mean, that's the easy way out. But really, you want to calculate the noise during timing propagation. But that's the right way to do it. And yeah, these are all the things that make the timing analysis much higher complexity, because you also have to go around multiple cycles. So your effective circuit size is actually much bigger, because the periodicity is not just one iteration. It may be, unroll, effectively it's like having a clock circuit that's been unrolled a whole bunch of times on which you need to do timing propagation, because you basically end up going through the same gate multiple times to get all the correct offsets. But yeah, so you would have to do noise propagation during timing propagation. That's the right way to do it. Yeah, that's a really good question.
Okay. Do we have any other questions?
Super interesting talk. I was curious, in your slide that had the pictures of tape outs, you mentioned you had a RISC-V 12 nanometer chip. What can you say about that now? Maybe
no.
Progress,
So
I guess.
I mean, sorry, I didn't really go through this. So these are preparatory tape outs. This is just to make sure that we understand everything we need to get right in the flow. So then,
okay.
So these are just simple RISC-V chips.
Okay.
Next year we plan to have the async versions of these chips taped out.
Oh, neat.
Right. So that's the idea. So actually, I have a student who's just basically used a hardware description language to write an asynchronous RISC-V. He's like, it seems to be simulating. So we'll hopefully do one of those sometime next year. That's the hope.
Exciting. That'd be really exciting.
Yeah, no, I'm excited. I mean, I'm actually very happy. I mean, it's kind of fun because, what I didn't say was all the chips we did before we put this flow together were mostly done full custom. Okay, so that gives you some idea of how much work it took to put out a chip. And it's really funny. So, there's one of the most complicated neuromorphic chips is something from Intel called Loihi. I don't know if you guys are familiar with this field, but I mean, my student wrote basically the pipeline version of that tile with the network of the Loihi chip in our asynchronous description language in about 2 weeks. It's not exactly the same. There are some bells and whistles there, but I mean, basically, there's nothing that in our design that the difference between our design and Loihi, yes, some people will argue about it, but from a computational perspective, really, we can do all the same stuff, right? But I mean, so it's not that hard to design. Once you've got the full flow going, it's amazing how much more you can do, right? I mean, the synchronous folks have been used to this for decades, but it's nice to finally get to the point where, this is within grasp for the asynchronous domain. But I mean, I would argue that one of the big things that is different, and I didn't really talk about this a whole lot, is what we figured out is a way to build one flow that can support all the asynchronous families I described. So as a result, it's actually then I think it's worth building the flow, because then even if we decide that there's a different circuit topology that's better, we know we can support it. If that makes sense.
Cool.
Right? So,
thanks. Yeah, it's great.
There's a question in the chat. It says, so you have your standard cell equivalent. Is that based on gas, 4-phase, 2-phase? Any more detail on that? Yes. So one of the things that our flow does is it actually, so you can decide whatever the hell you want. You can decide what your gates are. It's up to you. Okay, so it's very, very customizable. So you can build your logic synthesis engine, target your favorite circuit family. And then when you run through our flow, it'll say, okay, I have, I'll read in the standard cell description that I have. and it'll try to match the gates that you have against what's in the standard cell library. And then it will tell you, I'm sorry, you have the following list of missing cells. Okay. And we actually, I didn't talk about this, but we actually have a standard cell generator, which kind of works. I won't say it works. It does the placement of the transistors for you. It draws all the diffusion. It does all the stuff except, and it partially does the routing of the wires. And then you have to finish the cell manually. We finish quite a few of the cells, but some of the cells you have to finish manually. So essentially the idea is you use this to dynamically, you have a cache essentially of your existing cells. And if you have any new logic family, then you add to that cache and you build up your library over time as you need it. So that's essentially how we do it. And we have our own characterizer, so we can characterize all the cells that you just built. Right. So then once that cell is in your characterized library, then the next time you run anything that uses any of the cells that you already have, it'll just pick those up and use them. And in fact, this particular chip that we taped out, that's how we built the cell library. We started with an empty cell library, and then we ran the flow, and it says, well, you need, here are all the cells you need. And then we generated as much as we could, and then we had to fix up a few cells manually. And then, my student who did the cell library basically told me it took him a week to create the cell library for this tape out. So that was actually, that's perfectly acceptable in my book. It turns out that doing the cell wiring is a non-trivial exercise if anyone has ever tried to do it in any technology after like 0.35 micron. In an older technology, we have automated routers that can route cells up to about 65 nanometer. At 65, it starts becoming painful. The library doesn't do a good job, but older stuff we can do, that's not so difficult. But starting at 65, the rule that really, for those of you who are layout people, is the min area rule that starts getting really, really upsetting if you're trying to write a cell detail router. But yeah, so that's essentially what we do for a cell. So, you can use whatever gates you want, whatever sizing you want, and we'll just assume that that's in your library. If we don't find it, we'll tell you and ask you to please give us your cell. That's essentially what we have.
All right. Well, thank you. That was an interesting talk, some good questions.
Great.
And yeah, I appreciate taking the time. It's kind of late for you over there, so.
Yeah, it's fine.
Yeah.
I haven't tried to cram so much into one talk in a really, really, really long time.
Yeah, no, I really like the overview approach, actually.
Yeah, it's a good overview for students who are not so familiar with asynchronous. So it's a perfect video to see.
Well, I hope people found it interesting. So, thanks.
Okay.
Thanks for having me. And if anyone has questions, feel free to email me and stuff. No problem.
Yeah, sounds good.
Thank you.
Yep.
Thanks.
Thanks.
Thank you.